Back from the break, and we're going to talk about the performance issues for the inverter again, but this time we're going to focus on the rise time. That's T sub R. So the rise time can be estimated quite easily in a similar manner to the fall time, and we're going to look again at the trajectory that we see as the device switches, and this is on the IV characteristics corresponding to the inverter, and we're going to be charging the load capacitor C sub L. So this is what it would look like. Initially we're at an output low. This is the output on the inverter, and it's held there because the PMOS device is cut off and the NMOS device is it is on hard, and it will keep the voltage at a output level low. We'll switch and basically turn the input on for the P-type device. So we're going to put the gate voltage to 0. We're going to turn on the PMOS device on hard, so it's in the saturation region. It's going to transition then into the linear region, and that'll continue to charge up the output capacitor until it's at VDD. So in this regime, we've got basically a current source charging the output capacitor. In this regime, we have a resistor charging the output capacitor. This is in a little bit more detail. This was point X1 prior to the charging of CL. The PMOS was cut off, and the output capacitance is maintained at 0 volts through the NMOS transistor, which is turned on hard. And you just recall that the NMOS is a pull-down transistor. It's very good for passing logic 0, and the PMOS is the pull-up transistor, very good for passing logic 1. This is our little schematic, and this is the state that we're at now, at this initial operating point. Then what we're going to have is we're going to transition to X2, and this is immediately after the input switches, so VDD will go to ground for the input of the inverter, and the PMOS goes into saturation. So we're in this region up here. The PMOS device will stay in saturation until the transition point, and this is where the PMOS device transitions from saturation to the linear region. So in saturation, the voltage is going to rise linearly, and when we're in the linear region, the voltage is going to rise exponentially. So from X3 to X4, PMOS switches into the linear regime as we talked about before. And the final operating point will be after the completion of the switching. The load capacitor CL is now fully charged to VDD. This is again a little bit of a summary of what happens. We have a situation where we turn off the NMOS transistor, turn on the PMOS transistor. It immediately goes into the saturation regime and charges up this capacitor in a linear fashion. So the voltage will scale linearly as you supply more current from the current source. Then what will happen is that the transitions into the linear regime, where the PMOS transistor looks like a resistor, and it completes charging up this load capacitor as if it were an exponential increase in the voltage. So it looks like an RC time constant. So during charging, the PMOS initially in saturation, as we said, from X2 to X3, then PMOS goes in the linear region from X3 to X4. During the initial charge, PMOS in saturation, the PMOS looks like a current source charging CL, and that's a linear increase in voltage. V out increases linearly until VDD minus V out, the absolute value, is equal to VGS minus VTP. Said another way, as soon as VO rises above the absolute value of VTP, the PMOS transistor will transition into the linear regime. So it really doesn't stay in saturation all that long. And the load capacitance is charged to VDD through a resistor. That's the linear regime for the PMOS transistor. So during the charging of CL, well, we already said that. Anyway, it brings us to an in-class assignment 5.5. In what region does the charging of the load primarily take place? And some justification for that is going to be required. And I think what you'll find out is that the way that the figures are drawn are not all that accurate, and you maybe expect a little bit more of the charging in one or two of those regimes, and perhaps not the one that you might expect. Rise time calculation then is similar to the fall time calculation. We'd calculate TF1 and TF2, do the little bit of arithmetic, and make an assumption for VTP, the threshold voltage being perhaps 0.2 times VDD, and we come up with a very similar approximation that we saw for the fall time. So the rise time is going to be 4CL over beta P times VDD. So if NMOS and PMOS devices are the same W over L, so that means the drive of those devices, then our fall time is going to be approximately half of the rise time, and that's accounted for by virtue of the fact that the mobility of the electrons is approximately twice the mobility of holes. Whether it's 2 or 3 doesn't really matter. Roughly equal rise times and fall times, so often W of the P is going to be 2 to 3 times that of Wn. And you can check back at the layout pictures from Chapter 2 and the FinFET assignment, and you'll see that for the FinFET inverter, you typically had more fins for the pull-up than you did for the pull-down. And for the layout pictures from Chapter 2, you had wider devices in the pull-up than you had in the pull-down section. And like I said, this could be more reasonably somewhere between 2 and 3. And we'll take a quick break.